Okay, so here's my fourth attempt to record this after I had to end the last one halfway through, and then the one before that was eaten by the YouTube ether. So hopefully this all goes well. But anyway, last bit of material that we're going to cover, which is chapter 8, which talks about something that you've seen before in some form, namely Taylor polynomials for some function. So the general idea is that you consider polynomials kind of the absolute simplest type of function that you can talk about. Polynomials are kind of like the nicest sort of thing that you can hope to study from a function standpoint. Um, and so the question is, what happens when you want to do some kind of analysis of your function, but your function is not a polynomial? Well, in many cases, as it turns out, that even if your function is not a polynomial, so first thing that might pop into your head when function's not a polynomial is something like sine or cosine or log or e or so exponentials, log functions, trig functions, things like these, kind of the first things that pop into your head when you think of it as something that is not a polynomial. But as you already know, all of those things I mentioned um, actually do have what are called power series expansions, right? So this is coming from Calc 2. You knew, or you were shown in some form, that all of those things, although on the surface they don't look like polynomials, it turns out that they, with some assumptions, they are equal to, in some sense, a power series expansion. If you remember, a power series is like an infinite degree polynomial, right? In that way, there was a particular power series for those that I just mentioned called the Taylor series. And you might even remember exactly the form that it takes, or at least be able to somewhat jot down something that's pretty close to it from memory. Um, and so the kind of the thing that you got out of the Calc 2 understanding of Taylor's theorem was that for certain reasonable enough functions, you could approximate those functions by Taylor polynomials or with Taylor polynomials. And in that case that you could do that, those functions in question had what were called Taylor series expansions about some point. So that was more or less the main idea. So the kind of unifying idea is that I want to be able to approximate um, a generic function by some polynomials. So main idea, I want to know to what extent I can approximate a generic function f of x by polynomials. Uh, okay. Where this word approximate has a specific meaning, of course, what it means to approximate a function with another function, that's going to have a specific meaning. The idea is once we've defined that, I want to know to what extent I can take generic function and approximate it in some sense by polynomials. That's really what I want to know. Okay, so in order to talk about kind of my first notion of closeness of two functions, I need a definition. So beginning definition is two functions having order of contact, or have contact of order k, is the first notion I want to define. So let I be a neighborhood of the real number x naught. then two functions f from I to r and g from I to r are said to have contact of order 0 So they're said to have contact of order 0 at that point, x naught, if they are simply equal to each other at that point. So if they agree at x naught, they have contact of order 0. The idea behind higher order contact is that not only do they agree at this point, but their derivatives up to some order also agree. So that's the notion here. So for a natural number n, f and g have contact of order n at x naught. This is the thing we're defining. If they both have n derivatives at x naught, and all of their derivatives up to the nth derivative agree at x naught. Note, to make this efficient, this is going to include k equals 0, the 0th derivative being the functions themselves. So these are equal for all, so for all k between 0 and n. Okay. So just intuitively, what does this mean? So of course, saying that two functions agree at a point, you know what that means. That just means that if you're thinking of their graphs, they intersect at that point. But knowing that they have contact of order n, it's not only do they agree, but also their derivatives up to some order agree. So for instance, if you had an example of two functions that had contact of order 1, but say not 2, it means that their values agree at some point, and then the slope of their tangent line, or even their tangent line itself, was actually also the same at that point. So I'll write an example of that in a second. So, quick example. Let f of x be square root of 2 minus x squared, and g of x be e to the 1 minus x. Both of these defined on the open interval from 0 to root 2. Okay. Then f of 1 and g of 1 are actually equal. And f prime of 1 is equal to g prime of 1. You can check that really quickly. Okay. But f double prime of 1 is not equal to g double prime of 1. So they have contact of order 1, but not contact of order 2. So f and g have contact of order 1 at x naught, which is equal to 1, but not contact of order 2. And if you were to plot these, of course, exactly what this means is that they intersect at the point 1, 1, right? So the values of those things at 1 are both 1. So the point 1, 1 lies on the graphs of both f and g. And so not only does that point lie on both their graphs, but at that point, their tangent lines also match up. Okay, so that's what's meant here. So intuitively, in some sense, the higher order of contact, the closer these functions are at that point, right? That's intuitively what it is I'm trying to say. And you might say, well, might sound a little bit ridiculous because, of course, they're equal to each other at that point. So, it doesn't get any closer than that. That's not what I'm trying to say. What I'm trying to say is that we hope to make the local argument that if you have two functions that have, contact of order up to order n at some point, then the higher order contact they have at that point, meaning if we zoom out just a little bit, looking around that point, hopefully that means something about them being close to one another in some neighborhood of that point, right? Yes, of course they're equal to each other at that point, but we want to know something about a window, some window around that point. Okay, all right. So a couple of quick identities. Note that for any textbook uses the notation j here as the exponent, but so for any natural number j, if I take the derivative of the expression x minus x naught to the j, this is of course j times x minus x naught to the j minus 1. Okay, I think you all, that has been sufficiently beaten into your heads by now. Thus, of course, if you repeat this process by taking k derivatives of the same expression evaluated at x equals x naught, so if you take same expression and differentiate it, say L times, k times, and the exponent here is L. So if you differentiate this k times, evaluate this derivative at x naught, what do you get? So you get k factorial if k is equal to L, meaning you have differentiated it just enough times, right, so that the thing that is left over is exactly this k factorial, and 0 if k is not equal to L. Right. So there's still a term left behind that's going to zero this thing out when you evaluate at x equals x naught. That's all that means. Okay. All right. So now the proposition that's going to lead to us defining the idea of a Taylor polynomial is the following. So this seems maybe it seems a little deeper than it is, but as you'll see from the proof, or the quick proof I'm going to write down, it's actually not very deep at all. It's kind of the only thing that could work out in this way. And so there's the following proposition. So let I be a neighborhood. Let I be a neighborhood of the point x naught. Let n be a non-negative integer. Okay. So suppose that f from that neighborhood into the reals has n derivatives. Okay. Then there is a unique polynomial of degree at most n that has contact of order n with the function f at x naught. Okay. And this polynomial is defined by the following formula. So you are going to recognize this immediately. So this polynomial is defined by p sub n of x, which is f of x, f evaluated at x naught, plus f prime evaluated at x naught times x minus x naught plus, and so on, f the kth derivative of f evaluated at x naught divided by k factorial times x minus x naught to the k, and so on, all the way up to order n. So up to the nth derivative of f at x naught over n factorial times x minus x naught to the n. Okay. All right. So this is the thing that defines my polynomial. You might say when you first glance at this, like, where does this formula come from? But as you'll see in a second, this is actually kind of the only thing that could work here. This is called the nth Taylor polynomial, as you've already probably noticed. So I'll write that in a second. Let me do this proof. So just quickly, what is it that I'm proving? I have some generic function. It has n derivatives, and it's defined on some I that's a neighborhood of a point x naught. And I'm claiming that this is the unique polynomial of degree at most n that has contact of order n with the generic function I started with. Okay, so here's note. So definition. P sub n of x is called the nth Taylor polynomial. Of f at x naught. Okay. So that is my definition of the nth Taylor polynomial. Okay, so quick proof of proposition. So proofs is following. If n is equal to 0, it's obvious. Okay, so think about why that is. This is, I mean, if n is equal to 0, then there's not a whole lot of not a whole lot of freedom here you have in your choice. So then suppose that n is greater than or equal to 1. Then using that differentiation of powers formula and thinking about what this means, so if I take the kth derivative of my polynomial p sub n of x evaluated at x equals x naught, this is the kth derivative of f at x naught. So they have contact of order in just by definition, right? So they have contact of order in. So then the only thing left is to prove uniqueness. But if you take a generic polynomial and just write it out, then the only thing that it can be, right? So so for uniqueness, if p of x is some generic polynomial, say c naught plus c1 x minus x naught plus c2 x minus x naught squared, and so on. So this is just polynomial of degree n here. Then again, using the same differentiation of powers formula, because the kth derivative of this, the kth derivative of the polynomial p of x here, evaluated at x equals x naught, what is that? So I differentiate this. I take the kth derivative of this thing. What do I get? This is going to be, so evaluating at x equals x naught, all the terms greater than k in degree here are going to be zeroed out by this evaluation. So the only thing that I'm going to get here is going to be k factorial times the kth coefficient. Oh, but wait, like that's exactly what I expect it to be. So this is true for all k between 0 and n. So this is what I get. But oh wait, like this is some other polynomial that's equal to that has the same contact of order n. So what is this? This means that c sub k is actually f, or the kth derivative of f at x dot over k factorial. So the only possible thing this polynomial can be is the nth Taylor polynomial. So that's it. Okay. So as I said before, kind of the way to think about this is the Taylor polynomial is the only thing this could be. Okay. And so here's a list. I'm not going to write them out. There's a nice efficient list here in your textbook of examples of Taylor polynomials. So if f of x is e to the x, so just the exponential, you can compute its kth derivative, right? For any k is just e to the x. So its nth Taylor polynomial is exactly this thing that you're used to from Calc 2. So it's just my coefficients are 1 over n factorial is the nth coefficient here. If your function is the natural log of 1 plus x, then it's slightly more complicated formula that you get here. So this is its kth derivative is found to be this thing. You can quickly remind yourself why this is by take like 3 or 4 derivatives of natural log and remind yourself why this works out the way that it does. And its nth Taylor polynomial is given here. So you might recognize this as some kind of weird. In fact, right, you might remember a trick from Calc 2 and how you can use this to compute the actual sum of like the alternating harmonic series. It's one of the tricks you can use using this power series, or the power series that comes from this. Okay, so then cosine x and square root of x, here's a couple more examples. Again, you might remember cosine x and sine x off the top of your head. You can find this once you see, oh, well, actually I can compute these derivatives in terms of even and odd order derivatives, and then it becomes clear what this has to be. So this only is going to have even power showing up in its Taylor polynomial. The Taylor polynomial for sine only has the odd power showing up. You might remember that as one of the tricky things you could do to using these, again, the power series expansion associated with these Taylor polynomials. You could solve the basal problem, right? So Euler's proof or solution to the basal problem use these things. Okay. So this is kind of, I can compute these Taylor polynomials for all of these functions. What does it tell me? By this proposition that I just proved, it tells me that for all of these functions, this polynomial that I wrote out, and notice in each case I specified some point that I was expanding about. So in the example of e to the x, I did it at x equals 0. For natural log, I did it for just some x that's greater than minus 1. And I did it for x equals 0 and x equals 1, respectively, for cosine and square root of x. So then at those points specified, I have found a polynomial that has contact of order n with that function. And so, intuitively, we should hope that when you have two functions and they have high order contact at a point, then it's reasonable to expect that, the difference between the actual functional values near that point will be small, right? So if I is your neighborhood, then you would hope that that on I, you could think about those things being small. So what is the takeaway? Our hope is that on I, containing x naught being the point that we've written this Taylor polynomial for f expanded about. That's the terminology we'll use. You'll see why if you don't quite remember why that's the case from Calc 2. You'll see why here in a little bit. So our hope is that on an interval that contains this point where we've centered our Taylor polynomial, then basically near x naught, or at least on this neighborhood, the difference between the functional values in the function I started with and my Taylor polynomial are small. So we hope, our hope is that on I, f of x minus p sub n of x can be shown to be small. This is our hope. Now, I should emphasize this is our hope. This is spoiling a little fun here. This is not what we're going to be able to do in general, like in total generality. But this is our hope. If we can do this, we are very, very happy, especially when n is big, right? So ideally, this is when n is large or large enough, right? That's the idea. So when n is large and x is near x naught, okay, which is what I said in words, but it helps to see it written out here. So the idea is that since we're talking about this order of contact business exactly at the point x naught, our hope is that if we take an x that is close to x naught and the order of contact is large enough, right, so up to the 20th derivative, right, they agree, you would hope that this can always be shown to be small. So frequently we're going to be very happy, okay? So in fact, I need a little bit more room here. So oftentimes, this limit, the limit as n goes to infinity of this difference between functional value and value of its nth Taylor polynomial at x. So oftentimes this is equal to 0 even when x is not that close to x naught. So that's really nice, because in this case, as we'll see, we are going to say that this function f is equal to this limit as n goes to infinity of this p sub n of x in some way. So the bit of the course that had to be sacrificed due to the shutdown is chapter 9, which chapter 9 talks specifically about what it means to have a sequence of functions and what it means to take the limit of a sequence of functions. For us in this chapter, we don't need any nothing complicated coming from that whatsoever. This is exactly what you think it is. The limit as n goes to infinity of these Taylor polynomials is the Taylor series that you're familiar with. So take your Taylor polynomial that has degree at most n. Instead of having degree at most n, it's now not a polynomial, it's a power series. So it has, infinite degree. It's a power series, so it's a sum, from n equals 0 to infinity. Okay. So then what is the hang up then? So oftentimes we get this and we're actually really happy. Maybe I should write that here. This is nice. Okay, but in other times we're not nearly as happy because this doesn't work out nearly as well. Unfortunately, it is also possible that Taylor polynomials for some functions do not provide good approximations at any point other than x naught, no matter how big n is. Okay. That's unfortunate. Okay. All right. So I'm going to define something that is going to be what we go into immediately next. So this little block of text is important because there's a lot of intuition that is kind of sorted out here. So this is the absolute nicest thing. This is what's going to happen when you're talking about functions like e to the x, sine, cosine, natural log. This is exactly what's going to happen. So when this happens, we say a function has a Taylor series expansion about some point, and I'm going to go into exactly what all that means. But when you don't have this, so here's the thing, right? I'm not going to make any claim about what is more typical, but using some selection bias, this in a way is more typical for what you're going to encounter. Maybe I should say, like, if you're looking for nice things. But unfortunately, the existence of these functions that I'm going to talk about near the very end of this chapter, and I'm going to title that little blurb "Why We Can't Have Nice Things." The existence of these is really, really unfortunate, but at the same time, it's kind of like one of the key facts of real analysis. So as I've mentioned before, the subject that we're studying now is called real analysis, to contrast it with complex analysis. So real analysis of a function, of real valued functions. Or I should say, analysis of real valued functions, or real analysis. So it is calculus where the functions are real valued. That's it. And so it is a defining feature of real analysis that there's some really, really nasty stuff that can happen with this sort of thing that doesn't happen in the complex case. So basically some equivalent facts to this statement where there's some weird function where things go wrong or things are nasty, that just doesn't happen in complex analysis. And I think I've hinted at that earlier in the semester. So the point is that for real analysis, unfortunately, there's the existence of these things, and it's just really, it really sucks on one hand, but it's also kind of the thing that makes real analysis what it is. So anyway, one more definition that I'm going to start on the next little bit, which is, definition, define, for a function, say I've already defined the terms using the exact same notation as earlier. I'm not going to rewrite all that. So define r sub n of x to be this difference. Okay, that I talk about above. So reformulated really quickly, we're happy when this remainder limits to 0. Right? We're happy when this remainder r sub n, well, I already spoiled what it's called. This is called the nth remainder. Okay, so define this for all x in your neighborhood of the point in question. So r sub n of x is called the nth remainder. Okay, you may even remember that from Calc 2, although that's typically one of the things that's glossed over very, very, very quickly. Okay, and so because we're very much interested in when this happens, we want to look very much at this expression more, and that's what the next chapter deals with. Okay, so there was a fact from chapter 4. Let's see, I think I barely have room here to write this. So recall from chapter 4, very end of chapter 4, I think I mentioned when I wrote this out that essentially the only reason I was writing it out was because we needed it later. So now is later. So recall from chapter 4, as a consequence of the Cauchy mean value theorem. This is really kind of the main reason we had the Cauchy mean value theorem. So as a consequence of the Cauchy mean value theorem, there was this lemma. So the lemma is the following. Let n be a non-negative integer. I'm not even going to write out that it's an integer. I be an open interval. Okay, so suppose f from I to r has n plus 1 derivatives. Okay, so suppose also that at x naught in I, the kth derivative of f at x naught is 0 for every k up to n. Okay. Well, I don't quite have the room that I think I can fit it here and it be readable. So then, for every x that is not equal to x naught in I, there is a point, so there exists C strictly between x and x naught. Okay. At which, let's continue on to another page so I don't really jam it in there. So at which what is true? At which f of x is equal to the n plus first derivative of f at c over n plus 1 factorial times x minus x naught to the n. Recall one of your homework problems has you using this lemma in a pretty direct way. I think I talked about that during the first problem session. So this is the statement after all that. Okay, you get this fact. It turns out that this fact actually is exactly is pretty much, I'm going to say like 90+% of the next theorem, which is a named theorem that is important when you're talking about Taylor polynomials. So this theorem is called the Lagrange remainder theorem. You might even remember that name from Calc 2 if it was covered when you took Calc 2. So this is the Lagrange remainder theorem. Okay, and so what this says is under the same assumptions as the lemma. So under same assumptions as the lemma, so under the same assumptions as previous lemma, there's a point, there exists C strictly between x and x naught such that the following is true. F of x is equal to the sum from k equals 0 up to n of an expression that is kth derivative of f at x naught over k factorial times x minus x naught to the k plus this term that is the n plus first derivative of f at c over n plus 1 factorial times x minus x naught at n plus to the n plus first. Okay. So before you get sidetracked by the way that this expression is written out, notice a couple of things. What is this? Hey, what is this expression? Well, this expression is just the Taylor polynomial, right? It's just the Taylor polynomial. And so what am I actually saying here? Right? What I'm actually saying is that using the same notation that I used previously, I'm saying that this is my nth remainder. Okay, called the Lagrange remainder term. Okay. So that's what this is. Now, what is the proof of this? Well, the proof is actually use notation from earlier. And notice that R sub n of x satisfies the previous lemma. What I mean by satisfies is it satisfies all the hypotheses it needs to apply the previous lemma. Apply the previous lemma to it, and then that's exactly what you get. And it turns out that, and you might say, wait, this R sub n of x is defined as this difference, and then this thing is f, whereas the lemma in question is like self-referencing. There's an f here and an f here. If I applied the lemma to R sub n, then I should have a like R sub n of x here and an R sub n of x here. So like, how does that work? It's because actually when you compute these derivatives, R sub n of x, compute the derivatives of this thing, they're just derivatives of f. That's how it works. So you can look through that proof on page 203, but it's a really short proof. This is the easiest way to describe it in one sentence. That's exactly how the proof of this goes. And this is a really nice fact. So there's a couple of things here. So practically, what are you going to use this for? So one thing is that this is going to allow us to say certain things. Like this is immediately going to allow us to state, something close to, or basically exactly what Taylor's theorem is, which is basically the conditions you need for your function to to actually have a Taylor series expansion at a point. And it's that this remainder term goes to 0. Okay, so that's one thing. Kind of the quickest application of when that is just for a polynomial itself, right? So quick application. This is we'll call this a corollary. So a corollary of this is, suppose P is a polynomial of degree at most n, and let x naught be any point. It's a polynomial, so x naught can be any point in the reals. Then the nth Taylor polynomial for P at x naught is P itself. So a polynomial is its own Taylor polynomial. How does that work? Well, essentially what you do to apply this previous limit to it is, for f here, substitute your polynomial of degree at most n. And so what you get here is, this is P of x. This is this expression, which is P sub n of x, plus this remainder term, right? But what's the deal with this remainder term? Well, this remainder term involves an n plus first derivative. But this is a polynomial of degree at most n. And what's the n plus first derivative of a polynomial of degree at most n? 0. So this remainder term, I don't have to worry about it limiting to 0. It's just flat out equal to 0, right? So the proof is, note Rn of x is equal to 0 for P. So literally, looking at this theorem and seeing how to apply it, R sub n of x is equal to 0 for this polynomial. And so P of x is equal to P sub n of x. That's it, right? That is, in a way, this is kind of like, should be obvious that you have a polynomial And the nth Taylor polynomial is supposed to be the polynomial that is unique in some way, that approximates the function as close as a polynomial can, right? In some way. Maybe I shouldn't say it that way because that's not strictly true. But I should say this is supposed to be a thing that provides a good polynomial approximation. And if you started out with a polynomial, it makes sense that the thing that provides a good polynomial approximation is just the thing itself, right? So this is good. This is boding well for our intuition here. Okay. So a few more things then that I wanted to discuss. So practical applications of this. This is a major hint, hint, wink, wink for your final exam problems. So, question, what are some quick applications of this? You can use you can use this remainder theorem to prove some inequalities that maybe otherwise you wouldn't understand how to prove. So the answer is it can provide a novel way of proving certain inequalities. What do I mean by that? So, for instance, exercise, let's just have a quick look. Exercise 1 on page 207, right? Asks you to prove the following, that 1 plus x over 2 minus x squared over 8 is less than square root of 1 plus x, which is less than 1 plus x over 2. Okay. If x is bigger than 0. How does that work? Where do these terms come from? So these terms that you're bounding it by come from the Taylor series for square root of 1 plus x. This is the idea. Okay. So the idea is that you're getting it from the Taylor series for square root of 1 plus x, and this bound that you're getting has to do with the remainder theorem. So I'm going to do a quick example of how this comes into play, because there's actually a really cool application I'll do quickly, and then I'll mention another application that's just because it's interesting. But this is one particular this is not just one particular application. This is a very nice way to prove these things. This has a lot of different uses. There's a lot of cool inequalities like this that might be kind of hard to see how you'd prove otherwise. So this is pretty important. So that's one possible quick application of this. You will find this useful, I think, for some of the problems you have left to do. Here's another quick application. So quick application, and this was something that it might otherwise you might find it kind of hard to prove this. Fact, E is irrational. Might seem intuitively obvious that E is irrational, but how would you prove it, right? So you think about the traditional proofs of showing irrationality of some real number. So immediately what jumps into your head is like square root of 2, square root of 3, square root of 5. And you kind of remember the tricks that go into those proofs. But what's really nice about those proofs, of course, is you do ye old trick where you do it by contradiction. You assume that it's equal to some ratio, and then you arrive at what you want from there. But think about what you'd have to do for e, right? E is defined in a way that's so weird and so different from something like square root of 2, square root of 3, square root of 5. And if you know a little bit more about properties of real numbers, you might automatically also notice that E has a property that those others don't have, or I should say it backwards. Those have a property that E doesn't have. And of course, this is the notion of being a transcendental number. So all those numbers I mentioned are actually roots of a polynomial with integer coefficients, whereas E is not that. E is cannot be expressed in that way, and that makes using a proof like that a little bit trickier. So what would you have to do? Well, one way to do this is actually using the Lagrange remainder theorem. So basically, what do we do here? We say there's a couple of things. So basically, you can say like first, E is strictly less than 4. Okay. How do I know that? So quick proof. By definition of E is strictly less than, and the fact that the natural log is strictly increasing. E is strictly less than 4 if and only if 1, which is the natural log of E, is strictly less than the natural log of 4. And so if E is going to be strictly less than 4, that can only happen exactly when natural log of 4 is greater than 1. But natural log of 4 is just the integral from 1 to 4 of 1 over t dt. Okay, which even if you don't do anything, you can just say, like, if you don't want to evaluate this integral, this is certainly bigger than or equal to the lower Darboux sum of f for some partition p. You can choose whatever partition you want. Just partition the equidistant interval. So if you're going from 1 to 4, just 1, 2, 3, 4 works fine. This is certainly strictly bigger than 1. I'm not even going to write that out. At this point, you don't hardly need to say any more than that. But yeah, natural log of 4 is definitely bigger than 1 from that. And then there's the following. So second fact. For each natural number, so for all natural numbers n, and for all x in the reals but x not equal to 0, there is a C strictly between 0 and x such that e to the x is equal to 1 plus x squared over 2 factorial plus all the way up to x to the n over n factorial plus that last remainder term. So this is my nth Taylor polynomial, and this last term, of course, comes from my remainder. So this is e to the c over n plus 1 factorial x times x to the n plus 1. There we go. Okay. So what is the point of writing this? So this fact, where does this fact come from? This fact is just me literally plugging the function f of x equals e to the x into the Lagrange remainder theorem. That's all I've done here, right? This expression that I've just bracketed is the nth Taylor polynomial for e to the x. This is my remainder. And so this is just me plugging e to the x into the Lagrange remainder theorem. But what does this mean? So in particular, and here is what's important, because this is what shows you how to use the Lagrange remainder theorem to prove some of these tricky inequalities. So in particular, 0 is strictly less than e to the x minus this polynomial 1 plus x plus all the way up to x to the n over n factorial. And that is strictly less than 4 over n plus 1 factorial. So here is, all of this is a fact that I have boxed. Okay, so all of this is some fact I have boxed. The first part of this fact, if I'm thinking of proving this on the next page, the first part of this fact is just the Lagrange remainder theorem. So then where does the second part come from? Okay, so maybe I should say proof of second fact. Okay, so proof of second fact. So first expression for e to the x is simply the Lagrange remainder theorem. So it's the Lagrange remainder theorem applied to the function f of x, which is e to the x. Okay, so that's simple. All right, now by the first fact, what do we know? Well, by the first fact, e is strictly less than 4. Thus, 1 is less than or equal to, or here, I'll write it like this. I'll say 1 is equal to e naught, and e naught is less than or equal to e to the c, if c is some number strictly between 0 and x, which is less than, say, e to the 1, which is strictly less than 4. And that's true if c, which is strictly between 0 and x is less than or equal to 1. Okay. Thus, our inequality follows immediately from, I should say, follows immediately from the first expression. So, using this estimate, right, so using this estimate here, what do I get? I get that if I subtract off 1 plus x plus and so on all the way, so if I subtract this p sub n off, this is what I'm left with. So maybe I'll write this out, right? So the idea is that e to the x minus 1 plus x plus and so on all the way up, the nth Taylor polynomial. If I subtract this off, this is equal to e to the c over n plus 1 factorial x to the n plus 1, right? So then I use this estimate on e to the c, right, on both sides, and then, right, then I plug in 1 here, right? So if x is less than or equal to 1, then using the estimate that e to the c is strictly less than 4, this is less than 4 over n plus 1 factorial times, so this is times 1 to the n plus 1. So that's where this estimate comes from. Okay, and it's clearly positive here. I should say it's clearly positive. Why is it clearly positive? Well, looking at this expression, e to the x is equal to something. And if I'm taking x to be a positive number, then so all this is positive. So e to the x is equal to positive plus e to the c over positive times positive. So e to the x is equal to positive plus positive number. So if I subtract off this chunk, that's still positive. So the bottom inequality comes from that. And so that's what I get. The reason I wanted to do this out fully is so that you can see how this works, because this is very similar to all of the inequalities that you can show using Lagrange remainder theorem. Okay, so this is the expression that I get. Well, when I simplify it, I get this one, and this is what I need. Okay, this is what I need to be done. So how do I show that E is irrational? So now, fact, E is irrational. Okay, so I'm going to restate this thing. So suppose not, i.e., suppose E is equal to n naught over m naught for some integers. Okay, since we know E is positive, we could say that you know they're positive. Then using the estimate, when I say the estimate, I mean this one. So using this estimate, okay, what do I get? I get that 0 is strictly less than n naught over m naught. Here I'm plugging in x equals 1. So I get that 0 is strictly less than n naught over m naught minus, I'm plugging in 1 here, so I get 1 plus 1, that's 2. So this is 2 plus 1 over 2 factorial plus some other stuff all the way up to 1 over n factorial. I don't really care that much about this expression. And this is less than or equal to 4 over n plus 1 factorial. Okay, and this expression has to be true for all natural numbers n. Okay. Now, what I can do is I can actually multiply by n factorial. Why would I multiply by n factorial? I want to clear this factorial out from this denominator on the right-hand side of this inequality. So I want this to become an n plus 1 instead of n plus 1 factorial. And so to make that happen, I just multiply through by n factorial. So multiplying through by n factorial, I get 0 strictly less than n factorial times n naught over m naught. And multiplying through by n factorial here, I get minus n factorial. Again, I don't really care that much about what I write here. And that is less than or equal to 4 over n plus 1. Okay. But, so this I claim does it. Why? So what I do is pick, so again, this has to be true for all natural numbers n. So what I do is I take advantage of the fact that this has to be true for any n, and I pick an n that is strictly bigger than 4, and I pick an n such that n is bigger than or equal to m naught, whatever m naught is. I can definitely do that. Doesn't matter what m naught is. I can always do this. What does this show, though? All right, what do these two things show? Well, really, just what if n was like equal to 4 here? What's the what is this saying? What do I get here? So if n is bigger than or equal to m naught, then n factorial times n naught over m naught is an integer. Now this becomes important because I look at this term and I'm subtracting here a thing that has to be an integer, because I'm multiplying by n factorial. The largest denominator showing up in this expression is n factorial. All those get cleared out. All those denominators get cleared out. And so this entire thing in the middle must be an integer. But if I'm looking at n bigger than 4, for instance, all this is taking place between 0 and 4/5. So according to this estimate, I have now found an integer between 0 and 4/5. But no such integer can exist, so that's a contradiction. Okay. All right, so that's a really nifty use of this. The reason I went through that, other than it just being interesting, is there was a very critical use of this estimate, and this estimate came directly from the Lagrange remainder theorem. Okay, so again, you will find this useful for your own work. Okay. Now, a couple of things that I want to say. So I'm going to go into one more use. I'm not going to do it all the way out because it's a little bit more involved than I want to admit, or that I want to actually go through. But I will mention, at least the estimate that is crucial here. So another application, just because it's interesting, is an estimate on Euler's constant. So don't confuse this with Euler's number. Sometimes it's also called the Euler-Mascheroni constant or Euler-Mascheroni number. What this number essentially tells you is the growth of the natural log. So I'm going to define this gamma to be the limit as n goes to infinity of the expression 1 plus 1/2 plus plus 1 over n minus the natural log of n plus 1. Okay, so this is kind of a funky expression. It's essentially like some weird difference between this sum, 1 plus 1/2 plus 1/3 plus 1/4 all the way up to 1 over n, and natural log of n. I know that I have n plus 1 here. You can actually massage that a little bit, but the point is that this is measuring like the difference in growth between these two things in some way, right? Because this is like summing the terms in the harmonic series, and this is comparing that to the growth of natural log. Okay. So fact that you can actually prove with the Lagrange remainder theorem is that the Euler-Mascheroni constant is bigger than 0, and it's less than or equal to 1. Okay. All right. And so the proof, I'm not going to go through the whole thing. The main thing where it uses the Lagrange remainder theorem is the following. So it does a couple of applications. So one, Lagrange remainder theorem, it uses in a couple of ways. So first way that it uses is, I'll just write the main thing. So there's an estimate, okay, that says that the natural log of 1 plus x and x can be bounded between 0 and x squared over 2 if x is positive. So this comes from Lagrange remainder theorem. It might actually also be an exercise. It is. It's exercise 4. I don't think I assigned that one, but it's exercise 4 in 8.2. This estimate comes from the Lagrange remainder theorem, and this is kind of the key. This is the thing that finishes it. There's some kind of annoying bookkeeping algebra that needs to be done first, but this essentially does it. So the main reason I wanted to mention this, other than showing that Lagrange remainder theorem can be used here to finish this estimate, is is the following. Basically, there's an open question. So, what is the fact that was proved using this estimate? It's just that this Euler-Mascheroni constant is between 0 and 1. Okay, the question is, what is known about this Euler-Mascheroni constant, gamma? Well, not as much as you would think. So what is the open question? It is unknown till this day whether this Euler-Mascheroni constant or Euler's constant is irrational or rational. This would make you a very famous mathematician if you could answer this question. Okay, it is not known. And keep in, for those of you that know a little bit more about terms coming from algebra or number theory, like transcendental, you might know that it was actually a very tricky thing for mathematicians to show that E and pi were transcendental. It took a lot of effort. It wasn't done until almost the turn of the century. It was done in the late 1800s, I believe. So it took a lot of effort to show that pi and E were transcendental. But it had been known that those were irrational for a while. But this is not a question as to whether or not this thing is transcendental. It's whether or not it's irrational. So it's not even known if it's irrational or rational. So you should have a look. You can have a look at the Wikipedia page, for instance, on this. If you want to see kind of like a history and kind of some heuristic evidence one way or the other that supports one position over another. But this is anyway. This is one thing that's kind of neat. The main reason I mentioned this, of course, though, is just to see that this particular estimate on it, like what size it is, comes from Lagrange remainder theorem. So if you want to know more about it, unfortunately, you will need something a lot more powerful than Lagrange remainder theorem. Okay, so we only have a couple more things to say about Taylor polynomials. So a couple things here. So recall some definitions concerning series. All right, so namely, what it means to talk about a convergent series, right? So let a sub n from n equal 1 to infinity be a sequence. Define the series, which is the sum from, say, n equals 1 to infinity. Of course, you know that this doesn't have to begin at 1 of a sub n. So this is a series. From this series, I can define a sequence S sub k, where the kth term in the sequence is the sum from n equals 1 up to k of this thing, right? So this is a sub 1 plus a sub 2 plus and so on all the way up to a sub k. This is the kth partial sum. And so then we look at the sequence S sub k from k equals 1 to infinity. This is the sequence of partial sums. So all this is ringing a bell, I'm sure. And so what do we do? We say, maybe I'll just change it just because the textbook does. So here, I'm just going to rescale it at 0. It's a lot more convenient anyway. So there, 1 up to k. All right. So anyway, so we have kth partial sum is what we call. So this is the kth term in this sequence. The sequence of partial sums is the sequence taken all together. If this sequence has a limit, we say that the series converges, and if it doesn't have a limit, we say the series diverges. So you're familiar with that. And so you're familiar with that terminology. So if limit, or if, maybe I should just say, if this sequence converges, we write that the sum from, say, k equals 0 to infinity of a sub k is equal to this limit. So the limit, as we'll say, n goes to infinity of the nth term in the sequence of partial sums. I know I swapped the roles of n and k, that's fine. So k equals 0 to n a sub k here. All right. If not, we say the series diverges. Okay, so again, this is just to refamiliarize yourself with all this. So note, I can write my nth Taylor polynomial in truncated fashion, right? I haven't actually truncated anything. This is just abbreviated using sum notation. This is the sum from k equals 0 up to n of so the coefficients are kth derivative of f at x naught over k factorial times x minus x naught to the k. Right, here is my nth Taylor polynomial written using sum notation. Okay, that's how it showed up in the statement of the Lagrange remainder theorem. Okay, and so if x is a point in I such that the limit as n goes to infinity of p sub n is equal to some f of x that we are, or sorry, not some f of x, it's the f of x that is used to define this nth Taylor polynomial. We write that f of x is equal to the sum from k equals 0 to infinity, just like we did for the generic series, of the kth derivative of f evaluated at x naught over k factorial times x minus x naught to the k. So this is what we write. Okay. This is called the Taylor series expansion for f at x naught. Okay, so you've heard that notion before. Okay, so this is called the Taylor series expansion for f at x naught. Okay. Now, I'm going to write here in a second. I'm actually going to write it out. Like, when can we say this, right? We can't always do this. Okay, so we can do this when this happens. But when does this happen? Remember at the very beginning, in like the first 10 minutes of this lecture, we saw that this happens exactly when that thing we're calling the remainder term goes to 0. Okay, so when the remainder limits to 0, I have that the nth Taylor polynomial limits to x, and so this f of x is equal to its Taylor series expansion at x naught. Okay, so let me write that. So note, f has a Taylor series expansion at x naught if and only if the limit as n goes to infinity of f of x minus p sub n of x is 0, i.e. the limit as n goes to infinity of r sub n of x is 0. Okay, so it's exactly when that remainder term goes to 0. So that's what we have. Now, there's a theorem that gives a decent criterion for this happening. So quickly, there's a theorem. So let I be a neighborhood of x naught. Suppose f has derivatives of all orders at x naught. Okay. So suppose, though that's true. I don't need derivatives of all orders just at x naught. I actually need derivatives of all orders everywhere on I. Yeah, that's right. So suppose also that there are positive numbers r and m such that the interval x naught minus r to x naught plus r is contained in I, and that for all natural numbers n and for all points in that interval, we have the bound, or we have f and all of its derivatives are bounded in this way. Okay. Then this is actually enough to guarantee that our function f has a Taylor series expansion about x naught. Okay. And this is true in a radius that's this r. This r defines our radius where this happens. Okay. All right. Okay. So, this is going to basically give us the okay for some easy functions. This gives us a nice criterion for when a function is equal to its own Taylor series expansion in some window, right, in some ball, in some interval. And so this is the thing that tells you when a function has a Taylor series expansion about a point. Okay, and so in terms of series, right, this is a power series. This is a particular example of a power series. And so another way of stating this, forgetting that this is a specific kind of power series called a Taylor series, is this tells us that f of x is equal to a power series, okay, in some window. So locally, near some point, f can be expressed as a power series. Why is that nice? So again, going back all the way to the beginning of this lecture, a power series is just like a generalized polynomial. So a polynomial, you know what that is. A power series is just an infinite degree, in quotes, polynomial, right? So it's a polynomial-like thing. It's just there is no top degree. It just keeps going on, right? So a power series is actually pretty nice, and if you have a function that is defined as a power series, even in a small window, that means it's a pretty nice function, okay? And so to give you evidence of that, let's have quick corollary of this fact. Some of your favorite functions, of course, can be written as a Taylor series using this fact. So e to the x, you know what e to the x looks like. So actually e to the x as a power series coming from its Taylor series is the sum from k equals 0 to infinity of x to the k over k factorial. Okay. Now, you may, later in your math career, depending on the textbook you use, if you use, I want to say that if you use like Lang's complex analysis book, I think that one of the very beginning things is that he begins with this as the definition of e to the x. So if you wanted to, you could define e to the x to be this power series and derive all of the other properties of e to the x from it. Or you can do like we've done here, where e to the x and log are defined in terms of one another. So e is the base of the natural logarithm, and then you can still arrive at this place where we arrived that e to the x is this. And a lot of math books will kind of open up with this function and then saying that this is literally the nicest function in all of math. So this statement is basically the statement that e to the x is like the greatest function in all of math, and that's its power series. So cosine x, of course, you can do this for sine x as well. So this is the sum from k equals 0 to infinity of, this is alternating, it's minus 1 to the k over, it's only the even term, so it's 2k factorial, x to the 2k, right, for all x. Okay, and the reason why you know those are for all x intuitively is you know for a fact that e to the x and cosine x have no issues, right? And so if you're able to express them as power series, thinking about it a little bit, this is an expansion. Notice that here, our expansion, right, we don't have to worry about some finite radius thing, right? So you might remember topics like radius of convergence for a power series. For these, we don't have to worry about anything like that, right? So this is a corollary of that previous theorem because e to the x and cosine x both just directly satisfy the results or the hypotheses of that theorem. So both e to the x and cosine x satisfy the hypotheses of the previous theorem. Okay, so that's it. Okay, so a couple more things. So another theorem. For convenience sake, it's easier to expand this when using a shifted version, but natural log of 1 plus x is the sum from k equals 1 to infinity of this weird alternating harmonic series looking thing. Right, so this is minus 1 to the k plus 1 times x to the k all over k. Right. Okay, and this one does, of course, have a finite window. So this is from minus 1 to 1. Okay. So you can do this with a little bit of work in this theorem. If you want to see the actual estimate here on how this works, you should look at so proof. You can see this on pages 212 and 213, I think, do this. Okay. This is just providing us with the power series expansion for natural log. Of course, you might say I left out sine here. You know what it is, and you can prove it using the same fact that sine x satisfies the hypotheses of that theorem. So now you see why when I assigned you problems from chapter 8, and I assigned you like kind of a smattering of problems, kind of peppered throughout the sections, that why I said that chapter 8 is kind of done almost in one go, because some of the sections are really, really short. So there is the integral form of the Cauchy integral, or the Cauchy remainder. There is the integral form of the Lagrange remainder theorem, which is called the Cauchy integral remainder theorem. So I will write that out, but I won't really talk about it. It has a couple applications that I'm not going to go into. So one is for Newton's binomial expansion. If you want to know anything about that, you can have you can have a gander at that in the section, but I'm not super I'm not really going to talk about it much other than to just state it so that you've actually seen it. So note that by the mean value theorem, if f on some interval I is differentiable, then, for instance, f of x is f of x naught plus f prime of c times x minus x naught. And so if it's differentiable and its derivative is continuous, I have no problem writing this in a slightly more suggestive way, that f of x is f of x naught plus the integral from x naught to x of f prime of dummy variable t dt. Oh, excuse me. Okay. So, actually then, what I can do here using this expression is to kind of recast everything I said about Taylor series in terms of this little trick using the mean value theorem. Now, actually, the mean value theorem was kind of sort of the thing that gives us the Lagrange remainder theorem, because if you remember, Lagrange remainder theorem was just like a kind of sort of barely extension of that chapter 4 fact, whose proof was entirely the mean value theorem. So in a weird way, all this business with Taylor series kind of underpinning it is the mean value theorem. So it's kind of a real, definitely showing that the mean value theorem is very, very, very important. So anyway, there's the theorem. It's the Cauchy integral remainder theorem. Okay. And so I have the same, so assume the hypotheses of the Lagrange remainder theorem, but also I want my n plus first derivative to be continuous. So this needs to be continuous. If it's not, there's issues. So then, for each point in I, or x in I, my function f of x can be written as sum from k equals 0 to n of the kth derivative of f at x naught over k factorial times x minus x naught to the k plus 1 over n factorial times the integral from x naught to x of the n plus first derivative of f at t times x minus t to the n dt. So this might look kind of like a funky expression at first, but if you think about it for a second, this really is like some kind of weird integral form for this remainder, right? So the proof is actually not too bad. The proof is essentially, so proof, you can have a look at page 216. The proof is essentially the first fundamental theorem is basically it. And so main application of this is Newton's binomial expansion. which I'm not going to get into. It is nice and important, but I'm not going to mention it. I would have liked to certainly mention it in a standard class, but alas, that is not a luxury we had, and so I've had to skip it. It is nice though. So if you want to read the rest of 8.4, or sorry, 8.5, this is definitely interesting. Okay, and so we arrive at, even though it's the last thing, this is a very important thing. This example is an example that you should have that rolls off the top of your head, or rolls off your tongue, I guess, just as easily as any other like important counterexample. So another example of this is like the harmonic series, right? Is kind of like your canonical example of a series whose terms limit to zero, but the series itself diverges, right? That's one example I can think of. Or if I ask you for a function that's not integrable, what is like your trick, right? So the trick to come up with a function that's not integrable is pretty easy. Just think of your Dirichlet function, right? So pick a value, right, a, and pick another value, b. Don't let a and b be equal to each other, and let a be, so let f be a piecewise function that is equal to a if x is rational, and b if x is irrational, right? So long as a and b are different, that function doesn't have a whole lot of a hope of being integrable, right? So very basic counterexamples like that. So this thing that I'm about to talk about is essentially is essentially the, like, one of the most important counterexamples going forward in analysis. It is almost like not to oversell it, but it's almost like a foundational counterexample for real analysis. And it is the reason why doing calculus in the reals works the way that it does. Okay, so this is very important. Maybe I should call this at the top: why we can't have nice things in real analysis. Okay. So this is a theorem, fact, whatever you want to call it. Define the following function f of x to be a piecewise function. It is the function e to the minus 1 over x squared if x is not equal to 0, and it is 0 if x is equal to 0. Okay. Then the function f from r to r has derivatives of all orders. You can quickly find the derivative of this thing. It has derivatives of all orders. You are good to go. Okay. However, the only point at which f of x is equal to the sum from k equals 0 to infinity of the kth derivative of f of 0 over k factorial x to the k is at x equals 0. So the only time this function is equal to its Taylor series expansion is when x is equal to 0. I'm not going to go through the proof of this. So if you want to see the proof, this is in 8.6. So proof, this is really this is all of the contents of 8.6. This is the entire contents here. So what is this? What should we understand here? F has infinitely many derivatives but no Taylor series expansion. That might seem like a kind of misleading way to say this, because it's not that it doesn't have a Taylor series expansion, it's that it's not equal to what we're calling the Taylor series, right? So in the way that I phrased it earlier, that means it doesn't have a Taylor series expansion. Okay, there's another way of saying this using terminology that is canonical in the literature, and so here's some definitions. So definition, a function f from R to R that has derivatives of all orders is said to be infinitely differentiable. Another definition, a function, say g from R to R, that has derivatives of all orders, and g of x is equal to the sum from k equals 0 to infinity of the kth derivative of g at 0 over k factorial times x to the k for all x is said to be analytic. So, phrased in another way, a function g that has a power series or Taylor series expansion like this is said to be analytic. Okay? So, a function that has a Taylor series expansion about 0 like this is said to be analytic. A function that has derivatives of all orders is said to be infinitely differentiable. Let's go back to this thing that I've written here, this ultimate example. What is this ultimate example saying using these new words? F is infinitely differentiable but not analytic. That is the very important thing that is being said here. Okay. So this is the key. This f is an example of a function that is infinitely differentiable, but it's not analytic. So it has infinitely many derivatives, but it doesn't have a power series expansion about 0. Okay. That's the key. That is what's being said. Now, the converse of this is actually a theorem. So if you are dealing with an analytic function, so note, if g is analytic, and it's defined here, so note, if g is analytic, then g necessarily is infinitely differentiable. You can just differentiate its power series term by term. So analytic implies infinitely differentiable. But the converse is not true, as shown by the previous function. Previous famous function, I should say. Okay? That is essentially all of the material. Okay. Now, a couple of like one more thing that I wanted to mention. Um, so at the very end of chapter 8, the last section is the Weierstrass approximation theorem, which is definitely interesting. I won't. I'm just going to mention it right now. I'm not even going to write it down. What does the Weierstrass approximation theorem say? Um, Basically, it says that under very mild assumptions, there is some polynomial that approximates even just a continuous function in a somewhat reasonable way. But the thing is that the polynomial that satisfies this approximation is not in general a Taylor polynomial. And while it is a very amazing fact that this is true at all, I don't want it to confuse you into thinking that, like all continuous functions have something as nice as a Taylor polynomial approximating. That's certainly not true. It's nowhere close to true. But but the Weierstrass approximation theorem is kind of like a silver lining, if you will. It's a pretty amazing fact, actually. The proof takes up a few pages at the very end of chapter 8, but there was no homework questions or no final exam questions about any of that. So anyway, that is it. That is the course. So sorry that it took forever to actually get this finally recorded. It's pretty, actually, what I had to go through to actually get it recorded is pretty comical, but that'll be a story. If you all have me in the future, I'll have several stories about the fun of this semester, as I'm sure you all have similar struggles this semester. So anyway, that's it. So that's the lecture. I'll have the problem session at the time I mentioned, 1:30 p.m. on Tuesday, this Tuesday. So that's tomorrow. Now, but anyway, so that's it. So hope hope it was somewhat helpful.